an auxiliary lecture on the use of tables. Okay, so this is, of course, an important skill that you'll need to learn in Mean 315, Principles of Thermodynamics. We're going to use tables repeatedly throughout the rest of the semester. This particular stage of using the tables has us using the tables for two substances. One is water, and the second is R134A. We'll be using other substances throughout the semester, but those substances will either be completely liquids, completely solids, or a combination of, completely gases, which would qualify them to be ideal gases, which we'll talk about on Tuesday during the online lecture number 9. Okay, but for right now, what I want to point out is the order of of the examples that I'll be going through in this auxiliary lecture. The first example that I'm going to do is an example of R134A. Remember, that's the refrigerant substance. We're going to be looking up properties of it in the superheated vapor region, and I'll show you how we determine that. And we're also going to make use of what we call linear interpolation, which is something that we'll have to be very familiar with this semester. The second example is going to be water, and this is going to be in the saturated region, so this is now where quality is defined. And then the third example is going to be liquid water, where we impose something called the saturated liquid approximation, and I'll talk about what that is when we actually go through that example. One thing that I want to point out when you're determining properties of a system, a good rule of thumb is to follow these four steps. The very first thing that you want to do is determine the substance. If you don't know what the substance is, or if you determine the substance incorrectly, you're going to go to the wrong table, or you're going to go to a table when in fact you should be assuming that it's an ideal gas, for example. Okay, so whenever we have water or whenever we have R134A, we will almost invariably use their respective tables to look up their properties. But the first thing you have to do is determine the substance. Number 2, determine the phase. Once you know the phase of your substance, that's going to then allow you to do step number 3, which is to determine which table to use. And I'll tell you how to do steps number 2 and number 3 in each of the 3 examples of this lecture. And then once you do those first 3 steps, you can then proceed to determine the property. It's pretty straightforward at that point. Okay, so let's move on to our first example. So as was mentioned, the first example is going to involve R134A. And in fact, what we're going to say is that we have R134A at a pressure of 1.6 megapascals and a temperature, or excuse me, I'm not giving you temperature, I'm giving you specific volume, I apologize. A specific volume equal to 0.015 cubic meter per kilogram. And what you have to find is temperature. Okay, so you have these two properties. You know that the pressure is 1.6 megapascals, and you know that the specific volume is 0.015 cubic meters per kilogram. Okay, so following our rule of thumb, the first thing that we need to do is to determine the substance. Well, this is pretty straightforward. You're told that it's R134A, so that means that you're going to be using the R134A tables. Okay, so our substance is R134A, so we're going to use the R134A tables. Okay, no problem there. Okay, the not so easy thing, rule of thumb number 2, step number 2, determine the phase. Now this is where things can get pretty tricky, because just by looking at those two values, pressure of 1.6 megapascals and specific volume of 0.015 cubic meter per kilogram, you don't necessarily know what phase that substance is in. I mean, first of all, we don't have day-to-day interaction with R134A. These are in metric units, which we don't necessarily have a very good grasp on anyway. And you know, it's in, say, specific volume, right, which is even something that we have even less grasp on. So how do we determine the phase of this substance? The easiest way to do this is if we rely on our knowledge of the pressure, say, volume diagram or the temperature volume diagram. Now, because we're given pressure here, we're going to go ahead and plot the pressure volume diagram and see if that information can help us determine what the phase of the substance is. Okay, so let's go ahead and draw the diagram. So this is pressure here. And this is specific volume down here. And then, of course, we draw on here our saturation dome. Okay. And we know, for example, that our pressure is 1.6 megapascals. I really have no idea where that pressure is on this diagram, so I'm just going to arbitrarily say that this is 1.6 megapascals, okay, just to see what that tells us. So everywhere along this dashed line, the pressure is equal to 1.6 megapascals. Okay, now, the other piece of information that I can look up pretty readily is I can look up what the saturated liquid specific volume is at that pressure, and I can look up what the saturated vapor specific volume at that pressure is. Okay, so I can actually determine what these values are. Let me see if I can go ahead and draw this down for us here. Okay, and this is V sub F at a pressure of 1.6 megapascals, and this is V sub G at a pressure of 1.6 megapascals. Okay, so how do I determine what those values are? Well, I can do that by going to my saturation table, table A13, or excuse me, table A12, sorted by pressure, right? So how do I find VF and VG? Well, those are saturation properties. I can determine them from table A12, which is the saturation table for R134A, sorted by saturation pressure. Okay, so we say that our saturation pressure is 1.6 megapascals, and we look up what VF and VG are. So let's go to our table. Let's go to table A12, and we'll find a pressure of 1.6 megapascals, which is the same as 1600 megapascals. And let's see if we can find that here. So I'm going to switch to camera mode. Bear with me because this is requiring me to interface with technology here. So let's just see if I can do this. I'm going to hit that, and then I'm going to hit that, and then I'm going to find wherever my camera is. And this seems to be a mystery to me. Photography, that would make sense. Okay, here we go. Okay, so let's see if I can get this to show up properly. Okay, there we go. The lighting is a little bit bad, I apologize. Okay, so we're looking at that line right there. You see the 1600. Okay, let's see if I can zoom out just a wee bit further so you can see the top there. Okay, let's see if I can hold that steady. Okay. So if you're following along in your book, this is going to be page 930 in your book. If the page numbers aren't matching up, it's table A12. Table A12, saturated refrigerant R134A, sorted by pressure table. Okay. Okay, so we are at 1600 kPa, and you'll notice that when I go over, what's given to me in this column here is my saturated liquid specific volume, okay, V sub F, is given at 1600 kPa, and then right next to it is my saturated vapor specific volume, V sub G, at 1600 kPa. Okay, so those are the two values that I'm going to write down, 0.0009400, 0.012123. Okay, so let's go ahead and write those down. So V sub F, okay, this got mixed up just a little bit. Let me fix this for us here. There we go. That should be better now. Okay, so V sub F at a pressure of 1.6 megapascals is equal to 0.0009400, and V sub G at 1.6 megapascals is equal to 0.012123 cubic meter per kilogram. Okay, so now how are these two pieces of information useful? Well, the specific volume that our substance is at is 0.015. So our specific volume, V, is equal to 0.015, which you'll notice is greater than V sub G at a pressure of 1.6 megapascals. So if I go back to my diagram over here, this V sub G is equal to 0.012123, but our specific volume, V, is greater than that, 0.015. And because we're at a pressure of 1.6 megapascals, that means that we are right here. And so this is our state. So that means that my phase, I've just determined that my phase is a superheated vapor. And of course, for R134A, that means that I will now go to table A13, because that's where my property data is when my substance, when R134A is a superheated vapor. Okay, so that was step number 2, right? And actually step number 3. Once we determine the phase, that then allows us to determine the table. So we now know what table we go to. We go to table A13. Now we can do step number 4, which is to determine the property. Okay? So this is going to be a little bit more involved, because in terms of determining the property, when we go to that table, we'll find that we don't have a precise table entry for a specific volume of 0.015. And let's go ahead and show what I mean by that. Okay, so when we go to the table, okay, we're going to go to table A13. And what we're going to do is we're going to go to the pressure equals 1.6 megapascal subtable. Okay, so table A13, pressure 1.6 megapascal subtable in your textbook, that should correspond to page 932. Okay, if you're using a different book than the one that is prescribed by the class, then it might be a different page number, but it should correspond to page 932. If not, just find the pressure equals 1.6 megapascal subtable in table A13. And so what does that look like? Well, we can go ahead and go back to our camera mode. So let's go ahead and do that. We'll go back to camera mode. Getting pretty good at this. Not really. Whoops. Okay. Getting pretty good at this. Okay, so we're back now in our camera mode, and I am in table A13, superheated R134A. What do I mean by the pressure subtable? So you see how so this is a subtable, this is a subtable, this is a subtable, right? And they all correspond to different pressures, 0.5 megapascals, 0.6 megapascals, 0.7 megapascals. So we want to find the pressure subtable that corresponds to 1.6 megapascals, right? So we look further down the page, and here we've got 0.8, here we have 0.9, here we have 1.0, here we have 1.2, 1.4, 1.6. Okay, so our data is going to be somewhere in this set of values here, in this pressure subtable. Okay, now, so you also notice that each pressure subtable has 4 columns, right? There's this column, there's this column, there's this column, and there's this column, okay? And each of those 4 columns, so the first column, are identified at the very top page. So the first column is specific volume, the second column is internal energy, the third column is enthalpy, and the fourth column is entropy, okay? Okay, so now what we want to do is we want to zoom in and just remember that this first column here is the specific volume, okay? And we look down this set of data and we wait until we find 0.015. Remember that the other known property that we have is a specific volume of 0.015. So we're getting close, 0.014, 0.015215. So we're exactly at 0.015. So our value, our state, is somewhere between a temperature of, let me pull out a sheet of paper here, is somewhere between a temperature of 80 degrees Celsius and a temperature of 90 degrees Celsius, okay? But how do we know exactly which one it is? Because our value is 0.015, it's not 0.014362 or 0.015215. We have to determine precisely what that temperature is, knowing that our exact value is 0.015. So to do this, we do something called linear interpolation. We're going to interpolate between this value, 0.014362, and this value, 0.015215, to find our temperature at the given state. Okay, so let's go ahead then and go back into our little note taker program here. And I'll have to probably realign this fellow again. Okay. So let me just summarize what we just did there. So we found that a specific volume of 0.015 cubic meter per kilogram at a pressure of 1.6 megapascals falls between a temperature of 80 degrees C and a temperature of 90 degrees C. So what that means is that we need to Linearly interpolate. Okay, so what is the basic idea of linear interpolation? The basic idea is the following. Let me draw a diagram here and show you what we're actually doing. Okay, so essentially, if we were to plot, say, temperature as a function of specific volume, okay, and actually, let me just back up a minute here because yeah, okay, so we said that we want to find the temperature, okay, and so if I were to plot the variable that we want to find as a function of the variable that we know. So the variable that we want to find is temperature. So that's going to be on our y-axis. Okay, so this is going to be temperature over here as a function of the value that we do know, which in this case is specific volume. Okay. Now I can plot what the relationship is between those two properties based on the known values that I have from the table. Okay, what do I mean by that? All right, well, I know, for example, that at a temperature of 80 degrees Celsius, my specific volume is equal to 0.01436. Okay. Likewise, I know that at a temperature of 90 degrees Celsius, my specific volume is equal to, and again, I'm getting these values from the table, from table A13, 0.015215. Okay? Okay, so that creates 2 points in the plane for me, right? I have those two pieces of information, and so that fixes, say, this point, that's known, and this point over here. Okay? So linear interpolation does the following. It says, okay, I'm going to assume that there is linear behavior between temperature and specific volume between these 2 points. In other words, I'm going to assume that there is a straight line between those 2 points. And what I know, the other piece of information that I know, is that I know that the specific volume of my substance is exactly equal to 0.015. So that means that my temperature of my substance at that specific volume and pressure is going to be equal to whatever this value is over here. So this is my temperature that I want to find. In other words, I'm making the assumption that point is exactly on that line that I've drawn between the 80 degrees C and the 90 degrees C with the two known values of specific volume. All right, well, I have a line, and fortunately, we can very easily calculate the slope of the line, right? So the slope of any line is the rise over the run. So the rise, of course, is y2 minus y1 divided by the run, which is x2 minus x1, okay? And what we can say is that because the point that we're trying to find is on the same line as the point, or is on the same line between temperatures of 90 degrees C and 80 degrees C, that the slope in this section, so I'm going to call this slope M1, so the slope in this section here, we'll call that M1, is the same as the slope between these 2 points. Oh, I messed that up. Just a moment, please. And we'll call that M2. See if I can clean this up a little bit better here. That's not doing it. Okay, I think that might be clear, hopefully. Okay, so in other words, M2 goes between is the slope of the line between 80 degrees and 90 degrees C, whereas M1 is the slope of the line between 80 degrees C and the temperature that we're trying to find. Okay, so because we've established that, we can then say that M1 is equal to M2. Okay. And so what that means is the following. Well, the slope of M1 is T find minus 80 divided by 0.015 minus 0.014362. And this is all equal to the slope of M2, which I'll have to write on the next line because I'm running out of room here, which is 90 minus 80 divided by 0.015 215 minus 0.014 362. Okay? And now we can calculate that very easily, right? So we have one unknown, T find. We have one equation. And so our T find then becomes, so I have to pull out my calculator here. And we can calculate this pretty easily, right? 90 minus 80 is 10. So we have 10 divided by 0.015215 minus 0.014362, and then that's times 0.015 minus 0.014362, and then plus 80 gives us a temperature of 87.5 degrees Celsius. And that then is our final answer. That is now the property that we were trying to find. Our temperature is 87.5 degrees C when our pressure is 1.6 megapascals and our specific volume is 0.015 cubic meter per kilogram. Okay, so, and that's the idea of linear interpolation. Now the thing is that if you have a program that will do linear interpolation for you, if you have a calculator that does linear interpolation for you, by all means, just use that. You don't have to go through this whole rigor of writing it out if you don't want to. You certainly can if you want to, and you'll notice on the homework solutions that for the first few times that we do this, I'll probably write it out completely so that folks can become comfortable and familiar with it. But you'll be using linear interpolation quite a bit, so any means that you can implement to make it easier for yourself is going to help you out in the long run. Okay, let's then go on to our next example. And so if you recall, the second example that we were going to do now has us looking at not only a different substance, we're looking at water in this case, but we're also looking at the saturation region, so water in the two-phase region. So in this case now what we have is we have water, and we're told that water is at a temperature of 200 degrees Fahrenheit with an enthalpy that's equal to 1,000 BTU per pound mass. And we need to find both the pressure and the specific entropy, little s. Okay. Okay, so the very first thing that you're going to note is that we're dealing with English units here. And so all of your tables, you have a metric set of tables, and then you have an English set of tables. And the numbering scheme is the same between the two sets. The difference is that the English tables are appended with the letter E to identify them as being English units. Okay? Okay, so let's go through our rule of thumb. And the first rule of thumb, if you remember, the first thing that we want to do is to identify the substance. And again, this one is straightforward. Our substance is water, okay? And so we're going to be using our water tables. Okay, so identify the substance. The substance is water. And so we're going to be using the water tables. This may seem like a trivial task. You may be wondering, why does he have us do this? We're told it's water. We know it's water. The reason why I have you do this is because invariably every semester students will get sort of um, uh, railroaded, or it's not the right word. You'll get a train of thought that always has you consistently looking in the water tables to look up properties, but then you'll encounter a situation where you need to look up properties for R134A, but because you've been trained to always look in the water tables, you go to the water tables instead of the R134A tables. So I build this step in there to make you take pause to first think about what is the substance so that you go to the right tables. Okay, the second step, if you remember in our rule of thumb, the second step is to identify the phase. And again, now we're dealing with a substance that we are familiar with, and we're even dealing with units that we're familiar with, right? I mean, we have a pretty good appreciation for degrees Fahrenheit, but we have no idea how much enthalpy is in a unit of water. So, okay, we look at this and we say, well, it's 200 degrees Fahrenheit. It's water. It's boiling, right? Or excuse me, it's not quite boiling. Water doesn't boil until it gets to 212 degrees Fahrenheit. So, this is obviously a liquid. Well, that's true if we were at standard atmospheric pressure, right? But we don't know what pressure we're at. The only other piece of information that we know is that the specific enthalpy is 1,000 BTU per pound mass. So we have to use those two pieces of information, 200 degrees Fahrenheit and an enthalpy of 1,000 BTU per pound mass, to identify the phase. We're going to identify the phase the exact same way that we did in the first example. We're going to look now, in this case, at a TH diagram because we have temperature as our one property and we have enthalpy as our second property. Okay, why is this not working? There we go. Okay, and so we'll have temperature over here, and we're going to have specific enthalpy on our x-axis. Okay, and we'll draw our little saturation dome. There it is. So cute. Okay. And then we'll also identify that our temperature of the water is 200 degrees Fahrenheit. And again, I have no idea where 200 degrees Fahrenheit is, so I'm just going to arbitrarily draw it here. I could be wrong, right? And I might have to back myself out or change how I interpret it, right? We actually ran into that in class the other day. But at least now I can find out these other two pieces of information, right? I can determine what my saturated liquid enthalpy is, my H sub F, and I can determine my saturated vapor enthalpy, my H sub G. So this is going to be my H sub F at 200 degrees Fahrenheit. So this is going to be HF at 200 degrees F. And this is going to be my Hg at 200 degrees F. Okay, so I want to look up what those two values are. Now, in order to look those two values up, we're talking about saturation properties here. And so I'm going to go to the saturation tables to look up these two pieces of information. And because I have water and because I am given temperature, I'm going to find HF and Hg by going to table A4. I go to table A4 because this is my saturated water table sorted by temperature. Okay, so let's go ahead and do that. Let's see what HF and HG are equal to at 200 degrees Fahrenheit. Okay, so I'll switch to camera mode. Getting pretty good. Okay, so now remember that we're English tables, so we're going to go to the tables that have the E on them. So we're going to go to table A4E. And there it is, table A4E, saturated water temperature table. And we're at 200 degrees Fahrenheit, so we're right here. Okay. And remember now that the other piece of information that we're given is enthalpy, right? So we have the saturated liquid specific volume, saturated vapor specific volume, right? I'm looking at the, oops, I guess that thing is, I don't know why that's showing up there. I'm sorry about that. Let me lift this up a little bit higher. Let me pull this down so that I can do this with one hand. Okay, so if you look up at the very top, right, these two pieces of these two columns are the saturated volume columns. These three columns, there we go. These three columns are the internal energy columns, right? This one here is saturated liquid internal energy. This one here is U sub Fg, the difference between saturated vapor and saturated liquid internal energy. And then this one here is the saturated vapor internal energy. And then we have the same three pieces of information for enthalpy here, from the 168.13 to 1145.7. And then we have the same three pieces of information for entropy here. Okay? So we're at 200 degrees Fahrenheit, and the pieces of, and we have a known enthalpy. And so we want to find out what the saturated liquid and saturated vapor enthalpies are so that we can determine our phase. So that's this number here, 168.13 is the saturated liquid enthalpy. And this number here, 1145.7, is the saturated vapor enthalpy. Okay, so let's take those two pieces of information and go back into our problem. And so we can now write these values down. Let me fix this over here again. There we go. So our saturated vapor, or excuse me, our saturated liquid enthalpy at 200 degrees Fahrenheit is 168.13 BTU per pound mass. And our saturated vapor specific enthalpy at 200 degrees Fahrenheit is 1145.7 BTU per pound mass. By the way, if the page numbers are lining up between my page numbers and your textbook page numbers, this is page, I was looking on page 966. Again, hopefully the page numbers are lining up, and that's helpful for you. Okay, so now what that means is that this value down here is equal to 168.13, and this value is equal to 1145.7, and we are at 1,000, which is between those two values, right? So we're somewhere here at 1,000 BTU per pound mass. And lo and behold, we are right here, and also at 200 degrees Fahrenheit. So that means that our state is right there where that open circle is. we are a two-phase substance. We're in the two-phase region. So HF is less than H, which is less than Hg, which means that our substance is in the two-phase region. Okay? So, we determined our phase. Now that we've determined the phase, that necessarily means that we're also going to correspondingly use, so with this piece of information, what that means is that we're going to use table A4. And so we've done step 3. Okay? So now that we've hopefully I'm clarifying why it's so important to first determine the phase. Once you know the phase of your substance, then knowing which table to use is perfunctory, right? It just comes right out of knowing what the phase is. Okay, so now that we know that we need to use table A4, oh, and to be very rigorously clear, I'm being a little bit sloppy here, because we're dealing with English units, this is going to be table A4E. Okay. All right, so we're going to use table A4E. Okay, so now we have an enthalpy, but what we need to find out is our pressure, and we need to find out our entropy. Okay, so we have to, use this information to find P and the entropy S. Okay, well, pressure is straightforward, right? Because we're, in fact, a two-phase substance, right? So we're two-phase, okay? Or also known as AKA, saturated, right? Remember that when we say that we're saturated, it's the same as saying that it's a two-phase substance. That means, remember, that when a substance is saturated, it means that T, temperature, and pressure, P, are dependent or coupled. So I already know my pressure just by virtue of knowing what my temperature is, right? So Tsat is equal to 200 degrees Fahrenheit. And I can then go to table A4, E, and find out what my Psat is. So let me show you how you do that. We'll go to table A4E. Okay, so here we are in table A4E. Okay, and I scroll down until I find 200 degrees Fahrenheit. There it is. And that first column of data right after the temperature is listed is the saturation pressure, right? Saturation pressure. So these are the pressures that correspond to when the substance is saturated at that given temperature. So we're at 200 degrees Fahrenheit. So its pressure is 11.538 psia. So we are much lower than, well, not much lower. We're about 3 psi lower than atmospheric pressure. And so that's why we're boiling our substance less than 212 degrees Fahrenheit, because we're at less than atmospheric pressure. Okay, so our saturation pressure, so we've already answered that one. Our saturation pressure is, let me fix this again. Our saturation pressure is equal to 11.538 psia. Okay, so that one's done. Easy peasy. Okay, the next one's not quite so easy peasy. Okay, so we now also we have to find what our enthalpy is. Okay, so in order to find, not enthalpy, I'm sorry, in order to find the entropy, right, we have to first determine the quality. Okay, we have to use the quality equation to know what our quality is at that phase, or excuse me, at that state. And then once we know the quality, we can then go back and determine the entropy. Okay. Okay. So remember that quality, or the quality equation, basically looks like the following: we have the enthalpy is equal to the saturated liquid enthalpy plus the quality times this difference between the saturated vapor and saturated liquid enthalpies, right? So in other words, HFG is equal to Hg minus Hf, okay? And I'm just going to take a very brief aside to describe to you how this comes about, okay? Basically, where this comes from is the following. If I think about what the enthalpy of my system is, right, I have, and I'm going to think about this in terms of an extensive property. So I have the enthalpy of my system, okay, and because I'm two-phase, I have some components of my system that are liquid, and I have some components of my system that are vapor. And so I'll have this be just an arithmetic sum of the portion that's liquid, the enthalpy of the portion that's liquid, plus the enthalpy of the portion that's a vapor. Okay, so that's VAP, vapor. Okay, so take note that these are extensive properties. Okay, so I can write this then as the mass of my system, okay, or my total mass, times the enthalpy of my system, which I'm just going to leave as H, is equal to the mass of the liquid times the enthalpy of the liquid, which we know is HF, right? We use F to subscribe the saturated liquid enthalpy. Okay, so in other words, that portion of the system that's a liquid, its enthalpy is the same as the saturated liquid enthalpy. And that portion of the system that is vapor, that mass that is vapor, its enthalpy is the saturated vapor enthalpy. Okay, and so we have then plus the mass of the vapor times the enthalpy of the vapor. Okay, which we use Hg. I should have written this as Hg. I apologize. So this is Hg. And okay. So now we also recall that we have a definition for what quality is. We say that the quality is equal to the mass of vapor divided by the total mass. Okay, so I'm going to go and I'm going to divide each term by the mass of vapor. Okay, and then the other thing that I'm going to do is I'm going to remember that my total mass. So I'll write this on the next line here. So my total mass, M total, is equal to the mass of liquid plus the mass of vapor. And that's important because I can now basically say that my mass of liquid is equal to the total mass minus the vapor mass. Okay. Okay, so if I rewrite my total enthalpy equation, I have M total times H is equal to M total minus M vapor times HF plus mass of vapor times Hg. Okay. Okay, now I can go ahead and divide through by the mass of vapor. Actually, it'll be easier if I divide through by the total mass. So let me do that instead. So we'll divide through by the total mass, right? So we're going to divide U by total, mass total, and divide this by mass total, and divide this by mass total. Okay, so of course, mass total cancels here, and so all that we're left with on this line is the enthalpy H. Okay, and then here we have M total divided by M total times HF. So then we're left with just HF right here. And then we have M vapor divided by M total, which is the quality. So this is minus the quality times HF. And then we have plus mass of vapor divided by M total, which is also quality. And so times Hg, so we have plus quality times Hg. And now we can bring in our definition of HFG. So we recall that HFG is equal to Hg minus Hf. And now we can combine all of these terms and get the form of the expression that we're familiar with, which is that H is equal to Hf plus X times HFG. Okay? So I wanted to show you how you do that just so that you know where that quality equation comes from. It's not just something that we just randomly make up. It all relates back to this original form that we started with based on what the total enthalpy of the system is. It's this combination of the liquid portion plus the vapor portion. Okay, so let's now continue the example, right? So we have that H is equal to HF plus X times HFG, and so we can transform that as necessary so that we get X is equal to H minus HF divided by HFG. So now we can solve for our quality. So our H is 1500 BTU per pound mass, and our HF was 168.13 BTU per pound mass. And then the HFG is the difference between Hg and HF, but that's also tabulated for us in table A4E. So I'm just going to go ahead and write that down so that I just have one less computation step that I need to do. And so that's tabulated as 977.60 BTU per pound mass. If you're wondering where I got that number from, just look back in the same table where we came up with the 168.13 BTU per pound mass and the 1145.7 BTU per pound mass, and you'll see between those two numbers is the 977.60. Okay, so we can now go and calculate what our quality is. So 1500 minus 168.13, and then that divided by 977.6 gives us a number that is too high. Oh, I see where my mistake is. I'm sorry. I am saying that our enthalpy is 1500, but our enthalpy, I guess, is actually 1100. Right? Or no, 1000. Yeah, okay. I'm sorry. I didn't mean to mess you up there. So this is not 1500. This is actually 1000. My apologies on that. Okay, so let me redo the calculation. So we have 1000 minus 168.13, and then that's divided by 977.6. Okay, there's a better number. So now remember that quality always has to be between 0 and 1. So our quality then is 0.85. Okay, and now that we know what the quality is, we can then take the quality information and we can go and calculate what the entropy is. And so to do that, we use our quality equation, only now we'll be writing it in the context of entropy. So we have S is equal to the saturated liquid entropy plus the quality times the SFG, the difference between saturated vapor and saturated liquid entropy. And so now I can look up what these two values are. And so SF at 200 degrees Fahrenheit, and again we'll find that in table A4E, same place where we found the enthalpies, is equal to 0.29409. And our saturated vapor, our SFG, so just go ahead and use that one. Our SFG at 200 degrees Fahrenheit is equal to 1.48191. I'm being a bit sloppy here. The units on both of these are BTU per pound mass Rankine. Okay, so now I can use that information to calculate our entropy at our given state. So SF is equal to 0.29409 plus our quality, which is 0.85, times our SFG, which is 1.48191. And when we plug this into our calculators, we should get a value that's equal to 1.554 BTU per pound mass Rankine. Okay, and then that completed step 4. That was finding the property. Okay. Okay, so now, and by the way, there are times, so if you look, for example, in the table, so if I switch real quickly to the camera mode and I take a look at the table here, there are certainly going to be times, we try to avoid them, but there are going to be times when you may have to linearly interpolate between within the saturated table. So for example, we have an entry for 160 Fahrenheit, we have an entry for 170 Fahrenheit, maybe we need to find the values at 165 Fahrenheit. Well, that means that we have to linearly interpolate between these two values. And if it requires us needing to know something like internal energy, for example, where you have to have the saturated liquid internal energy and the UFG, then you have to linearly interpolate between these two values. And so it can happen where there's a tremendous amount of linear interpolation. We always try to avoid that, especially on exams, but of course in practice you should know that that's a possibility, but it also could potentially happen on an exam as well, even in spite of our best efforts to try to avoid doing that. We certainly don't do that on purpose. Okay, so with that said, now we can move on to our third and final example, which is going to involve doing an important approximation that we'll often use in determining properties, and it's what we call the saturated liquid approximation. Okay, so this third example is going to explore what we call the saturated liquid approximation. Okay, oops, that's a little bit high. I don't know if y'all can see that or not. It says saturated liquid approximation. If maybe you can see it now. Let's see if I can drop this down a bit. Okay, let's hope that top bar should clear off there. There it goes. Okay, so what is the saturated liquid approximation? Well, let's find out by exploring an example. So in this example, what we're going to do is we're going to look at water, again our substance. And in this case now, water is going to be at a temperature of 20 degrees C and a pressure of 200 kPa. Okay, and what we need to do is we need to find the specific volume, V, and the entropy, S. Okay, so let's suppose that we don't know that we need to employ the saturated liquid approximation, right? I mean, and again, let's just look at, before we even start writing things down, let's take a look at the properties that we're given. We're told that water is at 20 degrees C. Well, it's a metric unit, and it may not be obvious to you, but 20 degrees C is basically room temperature. We know that water, under standard atmospheric conditions, is a liquid at room temperature, of course, right? Well, we're also told that the pressure is 200 kPa. Now, the other thing that you may not know is that atmospheric pressure is roughly 100 kPa. And so you may be thinking, okay, well, we go from 100 kPa up to 200 kPa. We may not have a physical sense for what that means, but I know that I've raised my pressure. I know that my pressure has gone up. And if you just think about it intuitively, if you have a liquid at 20 degrees C and 100 kPa, and you increase the pressure, you pressurize it, right? Well, it's still at 20 degrees C, but it's at a higher pressure. You've compressed it. That's going to keep it a liquid, right? You're not expanding it, which would cause it to vaporize, right? You're not going to a lower pressure like we did, for example, in the previous example. So, we have a pretty good sense that this is a liquid, but again, if you don't see that or recognize that right away, don't worry about it, because, after we do our first step, right? So, what is our first step? Identify the substance, and of course, we know that this is water. And again, I want to try and get you in the habit of doing that so that you don't look up something in the wrong table. But then remember that our next step is to identify the phase. What is the phase? Okay. And let's suppose that we really just don't know, right? We look at, that 20 degrees C and 200 kPa, and it just doesn't click with us that's a liquid. That's perfectly okay, because we can still use our little trick, right? We can still say, okay, I've got now my two known properties are pressure and temperature. So just to make it easy, I'm going to draw this on a temperature entropy diagram, but don't make the mistake of drawing this on a temperature pressure diagram, because that's not going to get you anywhere. So we're going to draw this on a temperature entropy diagram, and we'll go ahead and draw our saturation dome. And what I'm going to do is I'm going to really emphasize that part of the curve. And the reason why I do that is because I want to point something out to you on that side of the curve. And so I need to create as much space for me to be able to do that. Now, the other thing I'm going to do is I'm going to say, okay, well, I know I'm at 20 degrees C, and again, I really have no idea where that is, so I'm just going to suppose that maybe this is 20 degrees C right here. And so that's my 20 degrees C, so I'll draw my isotherm, right? So everywhere along this line, the substance would be at 20 degrees C. Okay. And now the next thing that I'm going to do is I'm going to draw the line of constant pressure that corresponds to the saturation pressure at 20 degrees C. Okay, so that's going to look like this. This is my line of constant pressure, and because I'm drawing the line of constant pressure, note that I'm not necessarily drawing the line of constant pressure for 200 kPa. This is the line of constant pressure for the saturation pressure at 200 degrees C, right? So this is Psat, or at 20 degrees C, I'm sorry. This is Psat at a temperature of 20 degrees C. Okay. And I want to know what that value is. So let me look up that value. And to look up that value, I'm going to go to table A4, metric table, saturated water, sorted by temperature, because I know that it's 20 degrees C. And so when I do that, I find out that my saturation pressure is 2.3392 kPa. And that's from table A4. Which, again, if your page numbers are aligned with my page numbers, that would be page number 916. Okay? Okay, so when water is at 20 degrees C, it saturates or it vaporizes at 2.3392 kPa. But that's not where I'm at. I'm at 200 kPa. My pressure is 200 kPa. So let's draw the line of constant pressure that corresponds to 200 kPa. Now remember, the other important thing to note is that lines of constant pressure in this TS plane go up with increasing pressure, right? So my line of constant pressure at 200 kPa is going to be something like this. Remember that pressure increases. So this is P equal to 200 kPa because it's a higher pressure than 2.3392 kPa. Okay? Okay, well that's helpful because now I know which phase I'm in. I know I'm at 200 kPa. Everywhere along this line that I just drew is at 200 kPa, right? So everywhere along this line, the pressure of the substance would be at 200 kPa. So I'm somewhere on this line, right? But I also know that my temperature is 20 degrees C, so I'm also somewhere along this line. Well, I'm exactly where these 2 points meet, where these 2 lines meet, which is right there where the arrowhead is. Okay, so I'll go ahead and draw a dot there. My substance, the state of my substance, is right here. Well, that makes me a compressed liquid, right? So now I am a compressed liquid. So my phase is compressed liquid. Okay, so now let's think about this. I have a table for water, only for water, not R134A. I have a table for water that is called my compressed liquid water table, right? It's called table A6. So let's talk about table A6 a little bit, right? Table A6 is the compressed liquid water table. But let's take a quick look at that table A6, and you're going to find something pretty interesting, okay? When we go to that table, what you'll see, so now I'm in table A6 here, right? Table A7, I'm sorry. I need to fix that. That's terrible. All right. Let me fix that very quickly. Good grief. Table A7. Okay, sorry about that. Okay, now we can go and look at table A7. Okay, so table A7, right? And page 924, the page numbers are lining up. Compressed liquid water, okay? And you'll notice that it's organized the exact same way that the superheated vapor tables are because, again, we're not phase changing. So temperature and pressure are independent properties, right? So my water could exist at 5 megapascals at 20 degrees C, right? Or it could exist at 20 degrees C at 10 megapascals or 15 megapascals, okay? Okay, so, but that's what I wanted to point out to you. Notice what the starting pressure of the subtable is. It's 5 megapascals. That's 5,000 kPa. My substance, or our substance, since we're doing this together, our substance, we're near 5,000 kPa. We're more than one full magnitude, order of magnitude, less than where the compressed liquid water table starts, right? So this table starts at 5 megapascals. But we're at 200 kPa, or 0.2 megapascals, if you will. So what do we do? How do we determine the properties of water at this condition? Well, what we do is we make an assumption called the saturated liquid approximation. And what the saturated liquid approximation does is the following. Okay, let me write it on the next page, and then we'll come back to this page. The saturated liquid approximation does the following. Okay, so if the substance is a liquid, but is not at high enough pressure for the compressed liquid table, or a compressed liquid table doesn't exist, as in the case of R134A, then assume, oops, that's not how you spell assume. Assume the substance has saturated liquid properties at the substance's temperature. Let me rephrase that. Rather than saying, we'll say taken at saturated liquid properties taken at the substance's temperature. Okay. So now that we know what the saturated liquid approximation is, so what we're going to do is we're going to assume that water at 20 degrees C, 200 kPa has the same properties as if it were a saturated liquid, and take those properties at 20 degrees C. So in other words, so let me go back up a page now. What we're doing is we're saying, okay, we're going to assume that the substance has these properties right here at 20 degrees C, and so the entropy that we're looking for is going to correspond to the saturated liquid entropy at 20 degrees C, and the specific volume that we're looking for is going to be, I need to fix this window, I'm sorry. The specific volume that we're looking for is going to be the saturated liquid specific volume. Okay, so now what that means is we can just go to our tables, our saturated water table, table A4, and look these values up. And so when we make the saturated liquid approximation, then we're saying that V is approximately equal to V sub F at 20 degrees C. Always do it at the substance's temperature, never at its pressure, because your error would be worse. Okay, and so we can then go to table A4 and find 20 degrees C, and our saturated liquid specific volume at that temperature is 0.001002 cubic meter per kilogram. Okay, and our saturated liquid entropy, so our S, is going to be approximately equal to SF at 20 degrees C. Approximately. And I need to change this a little bit so that y'all can see this better. Okay, I guess that's not going to happen. Oh, that's definitely not going to do it. Okay, let me write it up. Let me write it up above so that you can see it. Okay, so I'll write it up here then. So our S is equal to SF approximately equal to SF at 20 degrees C, which when we go to table A4 at 20 degrees C, we find that this is equal to 0.2965 kilojoules per kilogram Kelvin. So this is from table A4, making the saturated liquid approximation. And that is also true for our specific volume that we came up with. This is also from table A4, page 916, making the saturated liquid approximation. Okay, so again, when you would employ this approximation is when you have a liquid, when your substance is a liquid, but it's not at a high enough pressure to be in the compressed liquid tables, and so you then make the saturated liquid approximation at the substance's temperature, and you take those properties, in this case V sub F at 20 degrees C and S sub F at 20 degrees C. Okay, well, I hope these examples have been helpful for you, and if you have any questions, please feel free to contact me either by email or stopping by my office, and I hope that you have a good day. Bye-bye.